Welcome back to the Deep Dive. Today, we're kicking off something really important for a lot of you out there. It's the Deep Dive's CSWIP 3.1 exam prep series. Now, we know getting that CSWIP 3.1 Welding Inspector certification is, well, it's a huge step. And the amount of stuff to learn can feel a bit much, right? So our mission here is simple. Be your shortcut. We want to give you those aha moments, make the complex stuff click so you walk into that exam feeling confident and really, truly well-informed. We're going to tackle some key multiple-choice questions, the kind you'll see on the exam. We'll break down the right answers, sure, but also why they're right, the principles behind them.
Exactly. And it's not just about rote learning for the test. It's about building a real, solid understanding. These ideas are vital for the exam, obviously, but honestly, they're the foundation for doing the job well, for safe, quality welding inspection out in the field. We'll connect the dots, give you a bit more insight into why these details really matter.
Okay, perfect. Let's jump right in then. First up, something absolutely fundamental for reading any welding drawing, or it twists people up sometimes. How can you tell the difference between an NSO weld symbol and an AWS weld symbol? Here are your options. A, the EN weld symbol will always have the arrow side weld at the top of the reference line. B, the EN symbol has the elementary symbol placed on the indication line lying above or below the reference line to indicate a weld on the other side. C, the EN symbol has the elementary symbol placed on the indication line lying above or below the reference line to indicate a weld on the arrow side. D, the EN symbol has a fillet weld throat thickness identified by the letter Z. What do you think?
Right. This one gets right to the heart of a key difference between the two big international standards. The correct answer here is option B. Now, the crucial thing to grasp is the placement of the what's called the elementary symbol. That's your basic shaped triangle for a fillet, square for a butt weld, and how it sits relative to the reference line, the main horizontal line, and importantly, the indication line. That's the diagonal bit coming off the arrow. In the NSO system, if that little elementary symbol is on the indication line and it's above the reference line, that specifically means the weld goes on the other side of the joint, the side opposite to where the arrow is pointing. If it's below the reference line, then it means the arrow side, and that's fundamentally different from AWS. AWS puts the symbol directly on the reference line above for other side, below for arrow side, but without that indication line step. The aha moment for a lot of people is realizing just how critical that placement is. Get it wrong, misread the standard, and you could put the weld in completely the wrong place. Costly rework or worse.
That is a really clear way to put it. So thinking about real-world stuff, what's a common slip-up you've seen inspectors make with this, even if they kind of know the rule? Where does it go wrong in practice?
Yeah, a common trap is someone who's maybe mostly used to one system, say AWS, trying to, instinctively translate any NSO symbol instead of properly applying the rule. They might see the symbol placement and just default to their usual interpretation, so they specify a weld on the wrong side or miss one intended for the other side according to NSO rules. I mean, I've genuinely seen fabrication held up because of confusion over just a few symbols. It really shows why you need to understand the why behind the difference, not just memorize a rule.
Makes total sense. It's about avoiding those big, expensive mistakes down the line. Okay, so from reading the plans, let's shift to what can actually go wrong inside the metal itself. Defects. This is where it gets really interesting. What exactly is lamellar tearing? Your options. A is a product defect caused during the manufacturing of certain steels. B is a crack type, which occurs in the parent material due to welding strains acting in the short transverse direction of the parent material. C is a type of hot crack associated with impurities, sulfur, carbon, and phosphorus.
D is a type of crack that occurs in the weld or parent material due to cyclic stresses.
Oh, lamellar tearing. Yeah, this is a really important one for inspectors. It's quite specific. The correct answer is B. What makes lamellar tearing unique is that it's a crack, yes, but it happens specifically in the parent material. Not the weld metal itself. The welding definitely causes it. Imagine a thick steel plate. When it's made, impurities, inclusions, they get rolled out flat, kind of like layers or lamellae. Now, when you weld on that plate, especially in thick sections or joints that are highly restrained, the cooling weld shrinks. It pulls. If that pulling force, that stress, acts perpendicular to those flat layers, that's what we call the short transverse direction, pulling through the thickness of the plate. It can pull those weak layers apart. The plate literally tears along those internal weaknesses. You get these characteristic step-like cracks. And what's really insidious sometimes is that the welding just exposes a weakness that was already in the parent material. It changes how you think about prevention. It's not just about the weld itself, but the plate material too. The other options describe different things. A is too vague. C is hot cracking, D is fatigue. Lamellar tearing is distinct.
That distinction seems absolutely crucial, knowing it's the parent material, not the weld. But does it ever get confusing in real life? Or is it usually pretty obvious once you know what you're looking for?
It can be tricky, definitely, especially if the tearing is buried inside the plate and doesn't break the surface. That's why understanding the mechanism, the short transverse stress, the susceptible layered material, is so vital. If an inspector sees cracking in, say, a heavy T-joint, particularly in a thick plate known to be susceptible, alarm bells for lamellar tearing should ring. It points you towards needing more investigation, maybe ultrasonics, to confirm what's happening beneath the surface. It helps you find the root cause, not just the symptom.
Right, pinpointing the actual cause. Okay,
Right.
so knowing what can go wrong inside the material, let's look at the tools we use, the consumables. Cellulose electrodes, they're kind of legendary, right? What really defines them? What are their key properties? Options are A, viscous slag, large volumes of shielding gas and UTS values above 90,000 psi. B, large volumes of shielding gas, high spatter contents, and hydrogen levels 15 milliliters per 100 grams of weld metal deposited. C, large volumes of shielding gas, hydrogen contents 15 milliliters per 100 grams of weld metal deposited and should be never baked. D, high spatter contents, high deposition, and large volumes of gas shield.
Ah, cellulose. Yes, they are unique. Think of them as, well, high performance, but needing special handling. Option C hits the nail on the head. Let's break that down. First, large volumes of shielding gas. This is a big one. The cellulose coating burns off really vigorously. This creates a very forceful arc, a strong gas shield, and gives them that deep penetration they're famous for. That's why they're often used for pipeline root passes, things like that. Second, and this is super important for quality control high hydrogen content, specifically more than 15 milliliters per 100 grams of deposited weld metal. The burning cellulose generates hydrogen. While that helps the arc, it also means these electrodes introduce a lot of diffusible hydrogen into the weld area. That hydrogen can cause cracking, hydrogen-induced cracking, or HICC, in certain steels if you're not careful. It's a defining feature you have to manage. And finally, the absolute key instruction. They should never be baked. Never. Unlike low hydrogen rods that you bake to drive out moisture, cellulose rods need that moisture and organic stuff in the coating, so it makes them work. Baking ruins them. The other options, they get details wrong, especially on hydrogen or baking.
That never baked part, combined with the high hydrogen.
Wow.
That sounds incredibly critical. So what's the most maybe counterintuitive mistake people make with cellulose rods that just wrecks everything?
Honestly, trying to treat them like low hydrogen electrodes, specifically trying to bake them. People sometimes think, oh, high hydrogen, let's dry them out. But it's completely the wrong thing to do. Baking cellulose rods doesn't lower the hydrogen in a useful way. It destroys the coating's characteristics. You lose the arc stability, the penetration, the gas shield. You just end up with poor welds. It shows a fundamental misunderstanding of how they're designed to work. So yeah, that never bake rule is non-negotiable for quality.
Absolutely. It's not just exam trivia. It's job site safety and quality. Okay, let's switch tracks again. Inspection techniques. Radiographic testing, or RT. Seeing the invisible. When you're doing RT, how would a lack of root fusion typically show up on the image? Your options. A. On a radiograph, lack of root fusion would most likely show up as a dark straight line with a light root. B. On a radiograph, lack of root fusion would most likely show up as a dark root with straight edges. C. On a radiograph, lack of root fusion would most likely show up as a dark uneven line following the edge of the root. D. Lack of root fusion cannot be seen on a radiograph.
Right, reading radiographs is a real skill, like being a weld detective. For this defect, option A is the one you're looking for. On a radiograph, lack of root fusion generally appears as a dark, straight line with a light root. Let's think why. RT uses X-rays or gamma rays. Where the rays pass through easily less dense areas like gaps or voids, it shows up darker on the film. Denser areas absorb more rays, appearing lighter. With lack of root fusion, you've got a gap right at the bottom of the joint where the weld didn't melt and fuse properly with the parent metal. That gap is less dense, more radiation gets through. So you get that characteristic dark, straight line running along the root. The light root refers to the properly fused metal on either side, which is denser and shows up lighter. It's quite a distinct signature. Options B and C don't quite capture it. An uneven line might be more like incomplete penetration, maybe. Indeed, is just wrong. RT is very good at finding this.
That visual description is incredibly helpful. It really is like a decoder ring. But given how complex interpreting these images can be, what's a common lookalike that even experienced inspectors might sometimes mistake for lack of root fusion?
That's a great question. Sometimes things like excessive root penetration or maybe root concavity, suckback, can look a bit similar if the image quality isn't perfect or the viewing angle is tricky. Both involve density changes at the root, but lack of root fusion usually presents as a sharper, more defined dark line, often with quite parallel edges, indicating that physical gap, that lack of joining. Excess penetration might be a wider, fuzzier dark area, and concavity a smoother, perhaps curved, dark indication. The key is really looking for that sharp, straight line representing the actual unfused land. Precision matters hugely.
Precision is definitely the name of the game. Okay, last question for this session. Let's talk standards, the backbone of everything we do. What does the EN 287 standard specifically refer to? Your options: A, welder approval; B, welding procedure approval; C, visual inspection of fusion welds; D, welding inspection personnel.
Okay, this is fundamental knowledge for any inspector. Straightforward but crucial. The correct answer is A. EN 287 is all about welder approval. This standard defines how you test and qualify welders for fusion welding of steels. Its whole purpose is to make sure the person doing the welding has the proven skill and knowledge to produce quality welds consistently. It's about the competence of the individual welder. And it's important to know how it differs from the others. Option B, procedure approval, that's covered by different standards like EN ISO 15640 qualifying the process. Option C, visual inspection, has its own standard, like EN ISO 114637, defining how to do the visual check. And D, inspection personnel, well, that might relate to standards like EN ISO 146731 for welding coordinators.
Right.
So EN 287, laser focus on qualifying the welder. It's a cornerstone for ensuring quality starts with the person holding the torch.
Right, making sure the person doing the job is properly qualified. So how does this one standard, EN 287, really ripple through the whole quality assurance process on a big project? What's its fundamental impact?
Oh, it's absolutely foundational. You can have the best materials, the perfect qualified procedure, state-of-the-art equipment. But if the welder hasn't proven their skill, according to a standard like EN 287, there's a massive weak link. This standard is like the first gatekeeper for quality. It ensures the human factor, the actual hands-on skill, meets a recognized, reliable benchmark. Without it, you're basically gambling on the most critical part of the process. It underpins everything else.
Absolutely. It highlights how crucial that precise, informed inspection is right from the very beginning. And that, I think, wraps up another really insightful deep dive. We've sliced through some key CSWIP 3.1 areas today, hopefully giving you some quick, useful insights, from spotting the difference in weld symbols, understanding lamellar tearing, getting the facts on cellulose electrodes, knowing what lack of root fusion looks like on RT, and clarifying EN 287. You're hopefully feeling a bit better equipped for the exam and for your work. Our goal is to help you be truly well-informed.
And if you just zoom out for a second, connect this to the bigger picture, all these standards, this detailed knowledge about defects, it's not just abstract stuff for an exam. It's literally the foundation of safety and reliability in so much of our world. Think about pipelines, bridges, buildings. Every weld counts. Every inspection matters. Which brings up maybe a final thought for you, the listener. How does really understanding the nitty-gritty of these codes and defects ultimately help build a safer, more dependable world? And what responsibility does that place on you as an inspector?
That's a powerful point to end on. It really underscores the importance of mastering this field. Thank you all for joining us on this deep dive. Keep digging deeper, keep learning, and keep putting that knowledge to work. We'll catch you on the next one.